Hi, this is Mrs. Secor. If you could find this page in your notebook, we'll do a few problems here with isosceles triangles. All right, the first one over here on the left, I see that we have two sides that are congruent. So that makes this angle be 32, since it's a base angle. And that adds up to 64. So if we take 180 and subtract 64, we end up with 116 for this angle. Now up here we have the vertex angle equaling 40. So 180 minus 40 will give us 140. And we need to split that with two angles. So wouldn't that be 70 here and 70 here? Splitting that because those are base angles. The next problem here. If this angle is 72 down here with this isosceles triangle, so is this one. And here's a right angle, and then we have another isosceles triangle. So we need these two to add up to 90 also, right? Because 180 minus 90 is 90. We'll split that in half. 90 divided by by 2 is 45. Okay, now we have something interesting. We need to find this angle. We know these three angles form a half circle, 180. So if we add 45 and 72, that gives me 117, and 180 minus 117 will give me my missing angle of 63. Oops, sorry about that. So this angle here is 63. Alright, if that's 63, so is this one. 63 and 63, that's 126. 180 minus 126, 54. The next problem. We have a regular hexagon. We know that sums to, let's see, it's regular, so 6 minus 2 times 180. That'll give me 4 times 180, which is 720. So if I take 720 and divide it by 6, each angle should equal 120 degrees. All right, if that's 120, and that's 90 right here, this angle here should be 30 degrees. That doesn't look good. 30. How's that? Okay. This one's 30 because it's an isosceles triangle, because we know this side's congruent to this side. And that's 30 because it says they're congruent. That makes a right triangle, giving W a value of 60. And if that's 60, then this one has to be 60 because we know this angle here equals 120. Another isosceles triangle. If this is 71, we know this is 71. 71 and 71 is 142, and 142 from 180 gives me 38. So this large angle up here is 38, but I want half of it. It's bisected. Half of 38 is 19. So x is 19. Also, when we drop in an altitude, we know this bisects this base, so this y would be 5. Here we have an isosceles triangle inside of another one. Let's start with the inner one. We have a right angle here, so that makes this angle here be 45, right? Because it's 90. If that's 90, then both of these have to add up to 90 and be equal, 45 and 45. Okay, so we have an isosceles triangle. If the vertex angle is 38 down here, I'm looking at the large triangle now. I'll take 180 minus 38 and I'll get 142. Half of 142 is 71. So the corner angles equal 71 of the big triangle. So if this equals 71, and I already have 45 degrees here, 71 minus 45 is 26, right? 26. Okay, next page. We have some corollaries or different theorems that relate to this idea of the isosceles triangle. An equilateral triangle is a very special isosceles triangle. It has 3 sides congruent. And we can say this about it. If we have a triangle and it's equilateral, the sides all the same, then we know it's also equiangular. All the angles are 60. Then it is equiangular. The converse is true. If a triangle is equiangular, then it is equilateral. If we have a triangle that's right, then those 2 acute angles have to be complementary. They have to sum to 90. We saw that in the last page. So if a triangle is right triangle, then the acute angles are complementary. Oh, sorry about that. Okay, now if we have 2 angles of a triangle that are congruent to 2 angles of another triangle, you know what? That third angle has to be congruent also to the other triangle. And then the third angles are congruent. Now also, if we have 2 angles and they're congruent and they happen to be supplementary, I mean they're supplements to each other, well, we know that they have to be 90, right? If they're both congruent, 90 and 90 will give me this supplementary angle of 180. Okay, so if 2 angles are congruent and the supplements, then we know they're 90 degrees. Okay. Another topic we want to talk about are mid-segments of triangles. Let's stop.